Okay, now I am going to imagine that I prepare a state. Okay, so how do I prepare a state? Well, I make a measurement. So, oh, let me change color. So I prepare the state psi is equal to 1, 0. So how do I actually do this? Well, I make a measurement, okay? I measure the spin along the z direction, and I find that the spin is plus 1/2. After I've gotten that value of spin along the z direction as plus 1/2, then I know with complete certainty what state I am in. This is the state that I'm in. So to say that I prepared that state, well, how did I prepare it? I made a measurement. I made a measurement. Good. Okay, now let's imagine that you are now going to make a measurement. You will now measure the spin along the x direction. Okay, so you will make that measurement. So first thing we can say is you will measure the x component of spin to be plus 1/2 with a probability P is equal to the mod squared of Sx equal to 1/2 into psi to the mod squared of that overlap. And we can easily calculate that. We have all of the states here. So the state with the bra with Sx equal to 1/2 is 1 over square root of 2. And then I need to take the transpose of the state sitting up here. So that's just 1, 1. And then I need to put in psi, which is 1, 0. So let's see what that is. Well, I've got 1 over square root of 2. And I've got 1 times 1 is 1, plus 1 times 0 is 0. This is just 1 over square root 2. And the mod squared of 1 over square root 2 is just 1/2. So you're going to measure Sx is equal to 1/2 with a probability of 1/2. Now, you will also measure Sx equal to minus 1/2 with probability P is equal to the mod of Sx is equal to minus 1/2 with psi squared. And let's see what that is. Let's plug the state in. So 1 over square root of 2, 1 minus 1, 1, 0. And doing exactly the same manipulations as above, you find this probability is also 1/2. Now that's good because the sum of the probabilities is 1, and you must measure either plus or minus 1/2. So these are the two possible values you could get with the two possible probabilities. Let's imagine you get plus 1/2. After your measurements, well, now the state of the system has changed. Psi is now equal to 1 over the square root of 2, 1, 1, because it's in the state which has Sx equal to 1/2. So now, after your measurements, the state of the system has changed, and this is what the state of the system has become. So what this means is, and this is the important conclusion, by measuring the system, your measurement has disturbed the state I prepared. And in particular, I can detect this if I now measure the Z component of the spin, then doing exactly the same kinds of calculations that we just said, I will find Sz is equal to 1/2 with probability equal to 1/2. But I will also find Sz is equal to -1/2 with probability equals -1/2. So by you measuring your observable, you have disturbed the value of my observable. And why did that happen? That happened because your observable and my observable do not commute. Okay? Good. So if two observables do not commute, measuring the first observable will disturb the value of the second observable. Okay. So now let's consider again this fact, but let's also put in relativity. So here's our space-time diagram, T and X. Let me put in also the world line of light. There's the one world line of light. There's the other world line of light. And let's imagine that you are sitting over here. So that red dot is you, and you have an observable O, Y. Okay? Let's put on a point A over here, and sitting at A, there is an observable OA. And let's put on another point over here, which is, let's call this point B. And sitting at B, there is an observable OB. Okay? Now, if you measure observable OA at A, if you measure OA at A, then, not even light can travel between you and A. You would have to travel faster than light to get to A. So whatever you do at your point, you cannot disturb what's going on at point A. And whatever is done at point A cannot disturb what's going on at your point. Okay? So if you measure OA at A, well, let me say this differently. Let me say measuring OY at the origin and OA at A don't affect each other. So if you measure OY at the origin, it cannot possibly affect the value of OA, and that would mean that OY and OA must commute. So measuring these two things will not disturb each other. But measuring OY at the origin, this could disturb measuring. I'm not saying that it will, but it's allowed to disturb measuring OB at B. And why is measuring OY at the origin allowed to affect the measurement of OB at B? That's because light can travel from the origin to point B. Light can travel between those 2 points. You could move between those 2 points. So something that happens at the origin could disturb what happens at B. So that means the commutator between Y, OY, and OB need not vanish. It is possible that making a measurement of OY will disturb a measurement of OB. We'll continue in a minute.